Morning. So today we are going to see about the unit commitment problem. So unit commitment problem is one of the important optimization problem in the power system, as like your economic load dispatch. So we have seen the economic load dispatch, how to solve the economic load dispatch. What are the some of the important techniques of economic load dispatch to solve the problem. We have seen some important techniques, not we have seen the entire technique. I said there are n techniques, n number of techniques to solve the economic load dispatch problem. You could not say like this is the one technique to solve the economic load dispatch problem. Similarly, you know the complexity of the economic load dispatch problem. Why? Because we are solving only with the 3 generating units or some few generated 2 generating units, 3 generating units. We have solved the problem, and that too the constraints is only 2 constraints we have considered. But practically speaking, there are some 10 important constraints are there. We have not included that those constraints, but we have included only some two constraints, and we have solved the certain problems, and we got some solutions also. You know, the time constraints we didn't taken because that is for say for example that whole fuel cost coefficient that is being given for a whole day or certain period of time only we have taken. Even say for example minute by minute you need to go for a dispatch, or half an hour once, or hourly you need to go for dispatch, then the complexity becomes very the problem becomes very complex. Why? Because normally certain period of time itself it is taking more time. So like if you go for hourly dispatch throughout the day, like 24 times you need to dispatch, and you need to think, and you need to commit the generating units. Okay, so now as of now we have seen only the dispatch. So now we have to commit the generating units. Okay, which generating units has to be committed to? Committed means which generating units has to be selected. Okay, for how many hours? Say for example 10 generating units are there. 10 generating units are there. First generating units it should on for some 2 hours. Second generating units it should on for 4 hours. Third generating unit it should on for 8 hours. Fourth generating unit it should on for 12 hours to meet out the demand. Okay, so now we are committing the generating units. That is called unit commitment problem. So unit commitment problem is defined as committing the generating units to meet out the demand, and also with the certain constraints satisfied. Okay, so whatever the constraints you are taking into the account, that constraints also you should satisfy. So simple unit commitment definition is very simple. Like from the name itself you can write the definition. So committing the generating units to meet out the demand and also with the certain constraints. So that is called the unit commitment problem. So this is a very important optimization. So if you go to our earlier classes, so I have given some introduction to optimization. Then only I have taken this economic load dispatch problem. If you know what is optimization only, you can understand economic load dispatch problem. If you don't know what is optimization, still it is a very boon for you to study. Okay, so it is one of the very important optimization problem in the power system operation and control. So what is the main objective of the unit commitment problem? Is to schedule the generating units online or offline. Okay, online or offline over a scheduling horizon. Scheduling horizon means throughout a period of time, say for example some 24 hours of time, such that the power production cost should be minimized, with the total load, with the load demand fully meet out, and the operation condition satisfied. So the definition of unit commitment goes like this. That is committing the generating units online or offline over a scheduling period of time. okay, over a scheduling period of time such that the power production is minimized, same like economic load dispatch. Okay, but here you are committing, there you are dispatching, here you are committing, that's all. To with the minimum cost, with the load demand fully meet out and the operation condition constraints satisfied. Okay, whatever the constraints is being in the operation, that constraints also should be satisfied. So once again, I'm repeating the definition. So unit commitment is defined as committing the generating units online or offline over a scheduling horizon or scheduling period of time such that the power production cost is minimized with the load demand fully meet out and the operation condition satisfied. This is the definition for unit commitment problem. So this is the computational optimization problem. Okay, and it constrains many constraints. It constrains many hard constraints. Okay, hard constraints is some of the complex constraints it consists of. So that's why this unit commitment, solving the unit commitment problem is very, very complex. It's one of the complex problem that you ever solved in your mathematics or something like that. Why? Because why I am telling very complex in the sense, so how early you need to commit the generating units, how early you need to commit the generating units. So which generating units should on for which amount of time, that is for 1 hour. 1 hour is okay. So say for example, demand is changing minute by minute, again you need to commit the generating unit, you need to increase the generating, you need to choose the generating unit so that it should meet out the demand, or otherwise like you for a 24 hours of a time. So 1 minute, so how many minutes in 24? 60 minutes into 24 hours. So the problem, and also if the generating unit increase, say for example 5 generating units itself complex, 10 generating units itself complex, we'll see. So if the generating units increase, say for example all over the state, all over the region, you are going to commit the generating units. So that might be one of the complex problem that ever solved. Okay, so why? Because the unit size also will be increasing. So the commitment also will be increasing. So we'll see. You know how complex it is. So the main purpose of unit commitment problem is to find the optimal subset among the subset which provide the minimum operating. Similarly, like economic load dispatch problem, what are the constraints in unit commitment problem? There are many constraints in the unit commitment problem. So here some important constraints is being given over here. So the first constraint is spinning reserve constraint. So what is spinning reserve? Already we have studied. So spinning reserve is nothing but the term used to describe the total amount of generation available from all the units synchronized. Okay, total amount of generation available from all units synchronized on the system minus the present load and losses that is being supplied. Say for example, so what is how to calculate the spinning reserve? Spinning reserve is nothing but whatever the generation that is not metered. Say for example, 1000 megawatt is the demand. So whatever we are generating is we are generating also 1000 megawatt, but in that generator some losses might be there. Okay, losses might be there. In turn, we are generating only 980 megawatt or 990 megawatt. So 10 megawatt is the deficit. 10 megawatt is the deficit. So that 10 megawatt you need to generate with some other generating unit so that you can meet out the demand. Say for example, in the substation, you will be having some spinning reserve generator. So that generator, how they will operate in the sense, they will operate at the whichever the time. Okay, say for example, sudden fault happened. The entire generation is not coming. So we have to manage for certain time. We have to manage for say for example, in that particular day, some public exam is going on, or in a particular day, some important meeting is going on. Okay, in 10th or your graduation or something important exams is going on from morning 10 o'clock to 1 o'clock. So you need to give the reliable power supply. That is, so due to some fault, okay, due to some fault, one of the substation is not receiving any power. Okay, not only that, so if one of the substation due to the fault not but it is you can easily rectify that fault within some 5 minutes of time. So what they will do is they will on, so another one incoming line you are getting, say for example 1000 megawatt is the demand for that particular substation. So in one line it is coming around 800 megawatt or something like that. In another line 200 megawatt is the fault, incoming is the fault. So you need to manage that 200 megawatt. So say for example in the ring connected system you are getting another some 180 megawatt like that. Another 20 megawatt is the deficit fault. But that fault, whatever the fault happened is that can be rectifiable within some few minutes. Okay, so in that few minutes they have to give the reliable supply. So in that scenario, what they will do is they will on the spinning reserve generating units. Okay, spinning reserve that is being generated by your diesel generator, or in generating units, generating station itself, that will be of some spinning reserve generating units. Okay, suddenly say for example hydropower station suddenly okay 100 megawatt is suddenly getting dropping due to some fault, a shaft fault, or some certain fault. Many faults are there due to some shaft fault or that valve fault, anything happening, and suddenly 100 megawatt is dropping. So we need to give the unreliable supply. So by that time what they will do is they will be having one spinning reserve generators that they will start for some only few minutes, not for a whole period of time, until otherwise that fault is being rectified. So they know how many minutes it will take to clear that fault. Maybe say for example the first stage is getting fault, second stage they need to start. So for starting second stage they will be they want to spend at least at most 10 minutes, okay, to start that all the penstock valves and all. So by that time what they will do is they will simply on the spinning reserve generating units for 10 minutes so that it meet out the demand. So that spinning reserve unit will be of your diesel generator. In substation also they are doing, say sudden deficit is there, some small deficit is there, okay, some 1 megawatt deficit is there, or 0.5 megawatt deficit is there, but you need to give the reliable supply to that particular area. Some important meeting is going on, some government meetings are going on. So in that scenario they need to give the reliable. So by that time they will be on the spinning reserve. So that is what they also said. So spinning reserve is a term used to describe the total amount of generation available from the all the units synchronized. Okay, total generation available from the all the generating. Say for example, I said only one generating unit. Say for example, the 10 generating units are there. Synchronized, it is generating 1000 megawatt. So all the units synchronized, that is spinning on the system minus the present load and the losses. So whatever the generation minus present load and the losses. Say for 1000 megawatt is the generation. So present load is 1100 megawatt, and some losses. Sorry, present load is also 1000 megawatt, and losses you take like 20 megawatt is the losses. So if you minus that 1000 minus 1020 megawatt, so 20 megawatt is the difference due to the losses. Some power losses might be there. So how to manage? By using the spinning reserve for certain times until otherwise other units to be started. So if the 20 megawatt is the deficit, immediately they will start another 50 megawatt generating unit, or some mini hydel generating unit, or some small generating unit might be there, that they will start. But by that time we need to give the reliable supply. So by that time you can on this spinning reserve. So that's what it is being said over here. You can read. Next, what is the next constraint? So first is spinning reserve constraints. So next constraint is thermal unit constraints. This thermal unit constraints we have already seen. Okay, so in thermal unit constraints, so thermal unit requires a crew. Crew means some certain people. Say for example, already I said you can't on the thermal generating units with some 10 peoples like that. Okay, minimum requirement you need 200 to 300 employees minimum. I'm saying to the maximum of 500 employees. So if you don't believe, if you go to any nearby thermal station and you see the roll call or in the they will do the punching not daily. So if you see the how many employees entering into a one shift, say for example 3 shifts they are going, no? So 8 hour shift they are going. So if you check how many crew, how many technicians or how many human resources entering into that particular thermal generating unit is minimum 300 people might be entering to operate a, say for example 1000 megawatt or 1500 megawatt to the maximum of 4000 5000 megawatt. So it might be depends on, so 5000 means again you need another 200 members, 500 members minimum required to operate that particular throughout that full thermal generating unit. So minimum some crew is required to operate, especially when turned on and turned off. So many processes are there. First you need to heat the coal, then a boiler has to be heated up, then from the boiler steam, superheated steam will be generated. So that steam will be passing through the steel tubes for some long distance. So again that steam again you need to preheat because to reduce the losses. Okay, otherwise the losses might be very heavy. Okay, if the law because we are not spending 1 rupee, so we are spending lakhs and crores of rupees to generate that particular to generate that particular units. Okay, so it is not an easy task. So you need to extract maximum. So stage by stage you need to extract all the heat. Then again, so many like readings like temperature, then pressure you should maintain. So many readings that crew has to be taken off, that the employees or technician. Okay, like a technical assistants, maybe technical assistants might be they might be noting down all the readings. What is the temperature? What is the incoming temperature of the boiler? What is the outgoing? Then what is the temperature of the superheater steam? What is the pressure that is being created? So everything is noted down. Okay, it might be not one stage, it might be of 2 stage or 3 stage like that. So minimum time, the minimum time required for the thermal generating units to start itself will be taking minimum time 1.5 hours to maximum of 2 hours. Okay, so 6 o'clock crew is entering to a shift now, they will be starting 8 o'clock only, or otherwise the previous shift members might be starting. So after this crew enter into that particular role, then they will relieve. Okay, they will not relieve just like that. So whenever that second shift crew will be entering into that unit, then that first shift crew will come out. Okay, sharply they might be not coming out. Why? Because this is not a very easy task. One thing failures na, the entire, say for example one steel tube, they didn't maintain the pressure correctly or didn't maintain the temperature correctly, so it is getting burst na. So again 1000 megawatt is lost for that particular day, because we are spending that much lakhs of rupees for a coal. Then 1000 megawatt is deficit, it is not being generated, means that is the huge loss for that particular generating unit. So it is they will do very so thermal generating unit, operation of thermal generating unit is very complex than any other generating units. You can easily manage with 10 people, you can easily manage hydro. With 5 people you can easily manage wind. With 5 people you can easily manage your PV solar, then some other generating. But thermal is very complex. So there are and a thermal unit can undergo only gradual temperature changes, and this translates into a time period for some hours required to bring the units online. Okay, so for coming that unit to online, it will take minimum some periods. I said no, 1.5 hours or 2 hours minimum it might be taking. As a result of such restriction in the operation of thermal power plant, so various constraints also might be arising. So one such constraint is minimum uptime constraint. So what is minimum uptime constraint is once the unit is running, it should not be on turned off immediately. So why? Because if say for example 1000 megawatt is in operation, okay, if you simply off, you should not like a normal switch off. We are going to switch on the fan and switch off the lights and all. No? So like that, we can't simply off the thermal generating unit simply like that. So minimum some time is required to turn off also. Immediate stop you can do. Okay, like immediate stop button will be there, that you can press, and the whole, but the boiler heating and all you can't stop. That will be running. But the thing is that only the pressure that steam the inlet to the steam valve is there, na? That tube you can stop. But other than that, the boiler you can't stop immediately. Why? Because it is burning like anything. Okay, 500 degrees Celsius, 400, 500, 600 degrees Celsius, it might be burning. Okay, so you should not, it is not like in our home, we are turning on our gas stove and turning off gas stove. Na? So that is very easy. With the burner, you can easily turn on and turn off. That is very easy. But the huge boiler of 500 degrees Celsius, the turning off is not at all possible. It is possible. It will take around 2 hours or 3 hours to turn off that boiler completely. So unit you can immediately stop. So what they are telling is once the unit is running, it should not be turned off immediately. Okay, so you should give some time to stop that particular generating unit. So what is minimum downtime constraint? Once the unit is decommitted, say for example, once the unit is off, some evening 10 o'clock, that particular, say for example, evening 10 o'clock, that particular generating unit is, they are planning to stop. So what they will do is, they will stop that generating unit slowly from 9 o'clock onwards. They will stop the cold intake to that particular boiler. They will stop stage by stage. Okay, stage by stage they will stop. Say for example, two stages, 2000 megawatt is running now. The first stage they will off, then second stage slowly they will off. So by the time also you can because the boiler will be heat, and so by the time also they will be on some small generators of some 200 megawatt, 300 megawatt, because the boiler is still, the heat might be there. So in that time you can produce some steam also. So they can utilize that steam for generating the some minimum amount of generators. Some minimum generators might be there. So that also they might be generated because they are maximum. So what they are telling is once the unit is decommitted, there is a minimum time before it can be recommitted. So after 10 o'clock it is being off. So there is a minimum time. Let all the process to be cooled. Say for example, boiler also might be cooled, and water inside the boiler, water inside that boiler also have to be replaced. Why? Because if it is not replaced, then that scale formation will be there in the boiler. So that also will affect the efficiency of the unit generation. It will affect the steam output. The steam output is directly proportional to power generation. So that is also will be affected. So that is what minimum downtime constraint. Once the unit is decommitted, there is a minimum time before it can be recommitted. So that is called minimum downtime constraint. So what is crew constraints? Crew constraints is nothing but if a plant consists of 2 or more units, that cannot be turned on at the same time. Okay, since there are not enough crew members to attend both units while starting. Say for example, 300 members is 300 members is going for a shift to run the 2000 megawatt or 4000 megawatt. Okay, so for sorry, 300 members. So for operating the whole plant, so minimum. So some people will be working in your coal yard. Some people will be working in the boiler unit. Some people steam unit. Then some people in your SCADA system, PLC SCADA system. Some people in the generating unit. Some people in the your online that monitoring system. So the crew might be separated, but to start that particular generating unit, say for example, one stage, if they want to start a minimum 100 people or 150 people minimum required to start a one generating. Okay, so for example, our demand is 2000 megawatts. So immediately we need to on second generating unit also. So again, we can't able to call another 300 members to come inside that particular generating units. We should not on that particular. Why? Because the cost might be increasing. We need to pay the salary and wages to the employees. So minimum, say for example, minimum 30,000 or 40,000 you are going to you have to give the salary to the employees, and yearly once TA and DA increment you need to give. So then only that workers will work. Then bonus you need to give for some festival season. So everything you need to give. So to maintain the crew is not an easy task. 300 employees you are running with that particular generating units, it is not an easy task. So another 300 members you should not able to pay. So what they will do is, first they will start first generating unit with a certain crew, and immediately some after 1 hour they will start. So similarly, they will start second generating units with the same employees, but few employees might be there for noting out all the readings, everything. But majority of the crew will move on to the second generating unit to start the second generating. So by that time, by end of 2 hours, both the generating units might be operating, to reduce the amount of the salaries. To reduce, if you want to start both the generating unit at the same time, it is possible, but another same crew, like 300 people, so minimum 200 people needed for to start the another second generating. So 300 plus 2, 500 employees you need to pay. Instead of 300 employees, 500 employees you need to pay. So that is also one of the complex crew constraints. So you need to manage with the whatever the crew that is being entered into a particular shift to run that particular generating unit. So that is called crew constraints. So another one concept is that is called cooling and banking. So cooling and banking is nothing but the first allows the unit boiler to cool down. Okay, after that after the unit is running, the boiler, what they will do is they will let the boiler to cool down. Then okay, heat back to the operating temperature in a period of the scheduled turn on. Okay, scheduled turn on, that is called the cooling. Okay, so once the boiler has to be cooled down. Okay, why? Because as I said, the entire water has to be replaced. Okay, once in a while, what they will do is they will replace that water. Why? Because if the hard water is there already, say for example, first shift they are entering. The first shift they are generating some 1000 megawatt like that. So some water is there in the boiler. Second shift people they are entering. They want to start another 2000 megawatt. Okay, say for example that first generating unit is completely shut down. Okay, shut down before 1 hour itself. Okay, so what they need to do is they need to replace all the water in that particular boiler. Then they need to fill new fresh water into that boiler. Then they need to start. If they start with the same water, now what happens is they can also start. Nothing a problem will comes, but that water already that is hot water. Okay, some because we are extracting steam. I think we have to go to chemistry. Already you studied what is soft water and hard water. So in that hot water, again you are generating the steam will not come with that much pressure and that much steam, superheated steam you can produce, but instead of, say for example, that superheated steam is of some 500 degrees Celsius, then if you use the same water, it might be the temperature might be dropping in the superheated steam. Instead of superheated steam, only steam, normal normal heated steam will be generating. That might be of 200 degrees Celsius. It might be of dropping. Okay, and also pressure to that steam also will be dropping. So pressure to the steam will be dropping now. So that is heating the turbine. That also will be getting down. So automatically this might be happening. So that is called cooling. So you need to allow the unit boiler to cool down, then heat back to the operating temperature in a time for a scheduled turn. So next, what is banking in the sense? Banking requires sufficient energy be input to the boiler to just maintain the operating temperature. So you need to maintain that operating temperature of the boiler. So that is called banking. Okay, simply like that, say for example, you are heating the boiler to certain extent, 600 degrees Celsius, then simply like that, you are not maintaining the boiler heat. So simply like that, you are going to second stage, you are maintaining the steam output like that. But you need to maintain that 600 degrees Celsius for 4 hours. The hydro constraints. What is hydro constraints in the sense? The unit commitment problem cannot be completely separated from the scheduling of hydro generating units. Okay, so why? Because why I am speaking more on the thermal generating units. You might have think like, why is Sir is speaking more on only thermal generating units. So thermal generating units, as I already said, that is one of the most complex generating units to operate and as well as maintain and all. So if you solve for the thermal generating units, so then hydro and renewable energy, whatever the scheduling, if you are going for, it's very, very easy. Once if you manage with the thermal generating, why? Because this is more costliest generating units what we are operating in the particular schedule. Okay, thermal only one of the costliest generating. Okay, majority. So nuclear also somewhat less costlier than the thermal generating. Why? Because the nuclear one time only they are buying the fuel. One time only they are buying that fuel. For that fuel is being utilized for 6 months or 1 year, like that. If they bought some 5 kilograms of that particular uranium or plutonium like that, that might be come for some 6 months or 1 year. It depends on the what amount we are buying. But thermal generating units, tons and tons of load is being dumped onto that particular generating units for power generation. So so why I am speaking more than that is only because of its complexity. So similarly, like that, hydro also hydro constraints also will be considered. So we have seen hydrothermal scheduling coordination. Okay, hydro and as well as the scheduling. So we need to less utilize the thermal generating units. So you have to maximum utilize the hydro generating units to meet out the demand. And also, that hydrothermal scheduling also, it is being considered for this. This is also one of the constraints. So also one of the constraints for this unit commitment problem. So this is the cooling and banking we have already seen. Next is must-run generating units. This is also one of the constraints. So what is must-run generating units in the sense? Some generating units are of must-run generating units that is being running during certain times of a year. Say for example, in a particular state or in a particular district, there are some must generating. So it will be running for 365 days now, almost 300 days or 320 days it might be running. So only some 1 month might be some 1 month for maintaining daily, some monthly 2 days or monthly 1 day. It might be going for maintaining, or otherwise 350 days only 15 days only it is not running. Okay, 15 days, 350 days. So how it is possible now? Due to the resources, and it should be run to for the voltage support also. Okay, voltage support also minimum. There are some generating units. If you take in a particular state, there are some minimum in each district or each regions. There are minimum certain generating units. They might be identified so that the voltage. So demand also might be set. Minimum demand might be satisfied, and also how to select that generating unit based on the resource zone. So that's what it is said in the must run generating. So some generating units are must gen status during certain times of a year for a reason of voltage support on the transmission network for such purpose, or as supplies steam for use outside the steam power plant itself. Okay, so some of the states there is some generating units only they are utilizing for reactive power generation alone. So in Tamil Nadu, if you see one North Madras thermal power station is there. So that North Madras thermal power station, how they are generating the power in the sense they are generating the power by using some waste plastics. So what all the waste plastics is being dumped in the city, Chennai city. So in that from that they are generating the power from that particular generating. So that 200 megawatt, I think so. 200 megawatt is separately, it is a reactive power generating unit. So that reactive power generating unit, 200 megawatts is always generating in that particular state to meet out because you know the what is reactive power. So if the only 200 megawatt only for reactive power generation alone they are utilizing for that particular generating. So like that, similarly, some other states might be also having this kind of must run generating units for generating reactive power alone. Like that, some must run generating units. So and also not only that is must run generating units, some generating units has to be run for voltage support also, and also for meet out the demand also in that minimum demand for meeting out minimum demand. Definitely that generating unit has to be run, then only you can generate the you can satisfy the demand easy. So next is fuel constraints we have already we have seen fuel constraints like fuel cost coefficients. Okay, so for if you are burning the fuel, then how the fuel cost coefficient will be changing, like already we have seen in thermal generating units already we have seen. That is called fuel constraints. A system in which some units have limited fuel or else have constraint that required to burn a specified amount of fuel in a given time presents a most challenging unit commitment problem. Okay, so some constraint that require to burn a specified amount of fuel in a given time, because 2 hours you need to after 2 hours you need to start that particular, say for example 1000 megawatt, in the sense you need to burn certain amount of this much tons of coal so that you can heat up the boiler to the extent of 500 degrees Celsius, to the extent of some minimum temperature is there now. I'm not telling every boiler should be maintained 500. It might be depends on each and every generating units. I'm telling an example. Some minimum temperature they have to maintain in the boiler, no? So for a given time they need to heat that particular fuel, so that only you need to get the you will get the specified temperature, or otherwise. So that is what the fuel constraints. So with this, next we'll move on to the unit commitment solution methods. Okay, so the commitment problem can be very difficult as the theoretical exercise. Let us postulate the following situations. How? So I'm telling the unit commitment problem is very difficult now. How it is being difficult, that you should know before solving the problem. So what we need to do is we must establish the loading pattern for M periods. Capital M periods, we need to establish the loading periods, and we need to we have n units to commit and dispatch, n number of generating units to commit and dispatch, and also M load levels and operating limits on the n generating units are such that any one unit can supply the individual loads, and that any combination of units also can supply the loads. Okay, so for this, now what we are generally doing is we are going for with the loading pattern of M periods, and we are taking n generating units to commit and dispatch. Now, we are going to establish the commitment by enumeration, that is number of combination that we need to try for each hour. How many number of combination we need go for each hours, so that our total cost is being minimized, and also with the satisfying all the constraints. So what is the number of combinations in the sense? C of n comma 1 plus C of n comma 2 plus C, up to C of n comma n minus 1 plus C of n comma n, that is nothing but 2 power n minus 1. So 2 power n minus 1 combinations we need to do for the each generating units. Okay, say for example, what is n comma j? N comma j is nothing but combination of n items, that is n generating units, that is being taken for j time. J time means j up to say for example j is equal to 1 to 24 hours of a time. So what is the combination? C of n comma j is equal to n factorial divided by n minus j into j factorial into j factorial. I think in combination combination and combination, we have already studied this this formulation in our earlier standards. Earlier in the schoolings itself, we have studied what is the combination of the n items. Like that, we already studied this equation. We might have come across, that is C of n comma j is equal to n factorial divided by n minus j factorial into j factorial, where j factorial is nothing but 1 into 2 into 3 up to j. For total period of m intervals, the maximum number of possible combinations might be of 2 power n minus 1 the whole power m. Okay, 2 power n minus 1 the whole power m, which can be become a horrid number to think about it. How it is being horrible now? Just take your scientific calculator. All of you take your scientific calculator and calculate it for, say for example, whatever the examples I am being given. You just take your calculator and you can solve. Okay, say for example, we are taking 24 hours of a period of time. Okay, 24 hours in a particular interval, because in a particular day, 24 hours. So, so eventually we are taking 24 hours of a period of time, and consider 5, 10, 20, and 40 generating units, and you can go for the combination. Combination we already studied, 2 power n minus 1 the whole power m. M is nothing but intervals. So m we have taken as 24 hours. So that is 24 hours. So take your scientific calculator and calculate it for 5 generating units. If you calculate it for 5 generating units, so n is 5. Okay, so 2 power 5 minus 1 the whole into 24. If you type that is in your scientific calculator, I think you are getting answer as to 6.2 something into 10 to the power of 35. I think all are getting the same answer. Similarly, you can try it for 10 generating units. Take your calculator and type like 2 power 10 minus 1 the whole power 24. Okay, so similarly you are getting 1.73 into 10 to the power of 72. Okay, next step, 20. For 20 generating units, what is the combination? 2 power 20 minus 1 the whole power 24. I think you are getting some values like this, 3.12 into 10 to the power of 144. Similarly, you type it for 40 generating units. 2 power 40 minus 1 the whole power 24. I think in your calculator, math error will come. In your scientific calculator, math error, it will come. Okay, or undefined, sometimes undefined also it might be coming. So why? Because it is very, very complex. You can't be able to uh, produce the combination. For 5 generating units itself, 6.2 into 10 to the power of 35. That is 6.2 into 1 into 35 zeros you need to add. So that many combinations you need to go for 5 generating units. For 10 generating units, 1.73 into 72 zeros. That many combinations you need to go for. You need to add 72 zeros in that. So that many combination you need to go for 10 generating units. For 20 generating units, 3.12 into 144 zeros you need to add. For 20 generating units, 144 combination, that is 312 144 zeros you need to add. So that many combination you need to go for 24 hours of a time. Okay, see, for 3 generating units for economic load dispatch, 3 generating units, time is not being mentioned. So that itself taking for us, like for solving that problem itself, taking minimum 20 minutes or 25 minutes to the maximum of half an hour. Okay, even if you go for 10 generating units, it might be taking another 1 hour, 1.5 hours. You need to solve that particular 10 generating. So in that, time constraint is not given. If suppose time constraint is being given, so that might be even 3 generating units might be a very, very complex problem in economic load dispatch with the time constraints. Imagine the same unit commitment you are doing for 3 generating units. So if you are doing for 3 generating units, 2 power 3 minus 1, the whole power 24, some values will come. Okay, so that many combination you need to go for 3 generating units. So this much complex the unique commitment problem having. For 40 generating units, your calculator is telling like undefined, like not specified or math error it is coming, because it is not being calculated in your scientific calculator itself. Then how you can solve with the pen and paper? Pen and paper, I think it might be taking more than a month, or if you are daily doing 20 hours in a day, even in a pen and paper, even for a month also you can't able to solve that problem. So like that, this much complex, this much combinations are there to solve this 40 generating units. So now you can know how much complex the unique commitment problem is. Okay, so so for solving this kind of problem, what we are doing is we are going for certain assumptions. We are going for certain assumptions for solving this problem, and we are going to solve this problem. Okay, so there are 3 types of methods, like 3 methods: priority list method, dynamic programming method, and Lagrange's Lagrange's relation method are there for solving this unique commitment problem. Okay, so one such easy technique is priority list method. So in priority list method also we are going for certain assumptions and we are going to solve the problem. Dynamic programming method is it is also one of the complex method, but what we are going to do is we are going for solving using this fuzzy logic method for solving the dynamic programming method, so that our problem we are going to program by using same fuzzy logic concept, and we are similarly we are solving using this dynamic programming method. And Lagrange's relation method we have already seen. Similarly, like that, we are going to frame the Lagrange's function and we are going to solve the problem. And for these 3 methods, what we are going to do is we are going for certain assumption and we are going to solve this problem. Okay, and then only we can solve this problem. One such easy technique is priority list